Professor Robert Shortkoff's group working on circuit QED and superconducting qubits. And then he joined JILA in 2003, and since then has been there as a professor and a fellow of JILA. So Dr. Lehnert studies quantum coherence in macroscopic mechanical oscillators, and his research involved development of quantum coherent networks of microwave signals for control and measurement, and also implement quantum limited measurements in astrophysics, especially dark matter detections. So his award includes Vannevar Bush Faculty Fellowship and the Silver Medal from Department of Commerce, and he's a Fellow of American Physical Society. So today, Dr. Lehnert will talk about exciting new science of quantum sound. So take it away.
Thanks very much. Thank you for the kind introduction. It's really a great pleasure to be back, if only virtually, to the University of Illinois. Today, I'm going to tell you about the emergence of a new science and a new scientific technology of quantum sound. And in particular today, I'm going to talk about the transition from a world of linear quantum acoustics to one of quantum phononics, where we really have access to individual quanta, individual excitations of sound. And by sound, I mean, the motion of some macroscopic lump of stuff, either as the vibrational modes of some thin, tightly stretched sheet of material, or the elastic waves moving through a crystalline solid. And before I launch into that, I think it's worth, at least in my perspective, saying that we have three technology domains that where we really have access to the control and measurement of individual quantum systems. And in my way of kind of breaking up the world, this would include photonic and optic systems, either neutral or trapped ion systems, and specialty electrical circuits, often, but not always, superconducting circuits, and usually operated at ultra low temperatures. And the kind of motivation right now for studying these systems, of course, is the notion that there can be a quantum advantage in the digital computers or in the simulation of physical systems, really from the fact that information in the quantum domain is fundamentally different than a classical description of information. But the early experiments that established the quantum control in these systems, those seminal experiments, they're over 40 years old now in many cases, and quantum computing was not the motivation then. In those days, there was technological motivation around making more precise sensors or better clocks, but also just a genuine scientific curiosity that the kind of laws of quantum mechanics, when describing the behavior of individual systems, they're more notably strange and surprising. They diverge most drastically from the classical correspondence limit. So really controlling individual systems at the quantum scale was something that allowed us to understand quantum mechanics outside of a kind of correspondence limit. And we take inspiration from that as we work to develop a fourth quantum science and technology domain, one based on acoustics and mechanics, basically sound in micromechanical systems or in acoustical devices. So in the inspiration side of things, we really ask ourselves, what's the biggest, most tangible thing I could imagine preparing in some manifestly quantum state, something which, unlike a classical description of the position of some harmonic oscillator in phase space, is just some point, and going beyond just the notion that would pick up a quantum blob of minimum uncertainty, but imagining a quantum superposition of two such states. That's the sort of what is the biggest, most tangible thing we could ever hope to prepare in a state like this? That said, there are technological motivations for bringing quantum control and measurement to these acoustical systems. And to think about that, it's worth thinking a little bit about the role that acoustical systems play in classical information processing. Our wireless and telecommunication devices, they are full of information processing performed in the acoustical domain, essentially because the speed of light and the speed of sound are so different. The speed of sound is 100,000 times slower characteristically than the speed of light. And consequently, if you would like to build a high Q resonant structure with a given resonant frequency, that object in the acoustical domain will be many orders of magnitude more compact, smaller than its electrical equivalent. I like to say that in the acoustical domain, the term microwave is not a misnomer. Microwave frequencies in free space, as electromagnetism, are meters or tens of centimeters long. Gigahertz frequency sound waves have wavelengths of about a micron. And for that reason, you can make, for example, very compact millimeter scale filters that have a extremely good ability to discriminate frequency. You can have a very flat frequency response in your filter over a narrow range, and then that frequency response falls off a cliff. And doing that in the electrical domain in something that would fit in your pocket is really not possible. So in addition to things like filtering, there's also timing. Basically, if you would like a cheap but pretty good clock, and you usually need one for every device, you do that with by counting the oscillations of one of these quartz tuning forks. And if you need to delay a signal where you kind of think about what you're going to do with it, that's often done in the acoustical domain as well. So can we bring this kind of information processing that's enabled by acoustics into a quantum regime? So in addition to the sort of signal processing components, mechanical systems, they have a special role in measurement. They have a kind of characteristic of universal transduction, by which I mean that if you can't think of any other way for the phenomenon that you'd like to measure to kind of detect it, usually you can figure out some way that it might exert a force on a little cantilever, and then you can detect the associated deflection. That's, of course, used to great effect in atomic force microscopes, and more niche but interesting application in detecting the 3D nuclear spin density to do something like magnetic resonance imaging at the nanoscale. And can we bring that notion of universal transduction and sensing into a quantum regime? With that context, I think those of us who are sort of physicists will often think immediately of the example of the detection of gravitational waves. The gravitational wave is, after all, a very energetic phenomenon, but it is absurdly weakly coupled to us. And pretty much the best idea that anyone has had is to figure out how to make the gravitational wave wiggle some thing in your lab and to detect the very, very tiny associated wiggles. The image here is this sort of historically interesting Weber resonant bar gravitational wave detectors. And I like this as an example of the kind of transduction property of mechanical systems for another reason. It was really in thinking about the role of measurement and quantum mechanics in detecting gravitational waves and things like resonant bar detectors that really forced physicists to develop the calculational tools around quantum measurement. the naive kind of von Neumann postulate of undergraduate quantum mechanics, it's not easily applicable to the idea of continuously reading out the position of a harmonic oscillator. And that led to notions of a standard quantum limit and ideas that that standard quantum limit could be beaten using quantum non-demolition ideas or back action evading concepts. In some sense, the motivation to develop a mathematics of open quantum systems was really one of the big motivations was this question of detecting gravitational waves acting on harmonic oscillators. All right. So I think with that as sort of an introductory motivation, you have to go do it. You have to say, I'd like to think about mechanically oscillatory structures, controlling and measuring them at the quantum scale. And the prominent idea for how to do that for a while now has been quantum optomechanics, closely related to things that happen in the LIGO gravitational wave interferometer, but just on a smaller scale. And then I'll tell you a little bit about its electrical analogy, which I call electromechanics. So it's a simple enough notion to say that if I'd like to detect the position of an object with high precision, one way I might do that is by bouncing a very good laser light field off of that object and just measuring the phase acquired in a round trip. And then I think the thing which is like maybe a little less obvious is that you can also control your mechanical oscillator that way. You can push on it using the radiation pressure, just the momentum kicks of light as they're reflected from a mirror, and a mirror that you might support on a soft spring. I think it won't be too much of a surprise to understand that although that force isn't very big, the radiation pressure forces are not large, they can be quite precise in the sense that your laser can be a very high energy, high intensity state with very little entropy. Nevertheless, you make the whole situation better if you use a second mirror and create a Fabry-Perot cavity, and then the photons get many bounces to acquire little phase shifts, increasing the precision of the readout and also exerting more force per photon. And that's essentially what sits inside of the arms of the LIGO interferometer. Each arm of the Michelson interferometer contains a very big Fabry-Perot interferometer. I think starting about 14 years ago, it sort of became a scientific activity to take these Fabry-Perot interferometers and shrink them down to very small scales, and in particular try to support the mirror on a very light mass and floppy spring. This is a picture from Marcus Aspelmeyer's group in Vienna, quite old now, but it shows a high finesse, a high reflectivity mirror sitting on a suspended piece of silicon nitride, and that just is a mirror forming a mass on a spring system. And out of the picture is a fixed mirror, and that makes a system like this. And with that, you can read out with high precision. You can control the quantum state of that mirror, including damping it and cooling it to its ground state. So kind of coincident with that work in optomechanics, my group was inspired to create its electrical analogy, to build inductor capacitor resonant circuits, resonant and microwave frequencies, where the capacitor was mechanically compliant, where it was some degree of freedom that could move, and in doing so would change the resonance frequency of that inductor capacitor circuit. And now you can control and measure the state of that mechanical oscillator by exciting the resonant circuit with microwave fields. And it's pretty clear that if you bounce a microwave field off this resonant circuit through this little kind of coupling element, it will acquire a phase shift that knows about the position of the mechanical oscillator through the fact that it's changed the capacitance. In addition, you're exerting a force. There's electrostatic potentials between the two metal plates in this capacitor. that are controlled by the intensity of that microwave field. And so in strict analogy to that optomechanics systems, you can build these electromechanical systems. And part of the motivation for doing so is it gives immediate access to the quantum technology of superconducting qubits. Everything about these kind of circuits is compatible with operations at ultra low temperatures, much below 1 degree Kelvin. And they talk in microwave fields, which is how you talk to superconducting qubits. That was part of our motivation for doing this. And here's a picture of the kind of devices we were making. They are essentially just implementations of that circuit schematic. They are inductor, capacitor, resonant circuits, where the capacitor is mechanically compliant. We zoom in on it, it's 2 metal plates, one sitting above the other, where the upper plate is freely suspended and able to wiggle up and down at a few megahertz, modulating the resonance frequency of this LC circuit. And then there's a transmission line that slides by, and that allows you to inject and extract microwave fields. The electrical circuit resonates up at some few gigahertz, where by virtue of refrigeration, it's in a quantum ground state. The mechanical oscillator is quite a bit lower frequency. And if you analyze this problem, you say, I want to think about this as 2 harmonic oscillators coupled to each other. And I want to think about that in a quantum language. You pretty rapidly encounter a small parameter. And that small parameter is the separation of the 2 plates. That's the kind of big number. And the small number is the 0-point motion of the vibration of that upper membrane, the 0-point motion of the drum-like mode of oscillation. That small parameter, what it means is that at a quantum scale, at phonons in the mechanical oscillator talking to photons in this circuit, the intrinsic rate at which those 2 systems exchange energy is a few hundred hertz. Let me first say that that's extraordinarily fast compared to what you might originally make. It's hard to make this number as big as 200 hertz, and yet it's still small compared to dissipative rates in the problem. Nevertheless, you can access kind of quantum things about a system like this by pumping the electrical circuit intensely and detuned from its resonance frequency. So in a frequency domain picture, just imagine that the electrical circuit has a resonance frequency in the gigahertz regime. Down here's the mechanical oscillator with its resonance frequency in the megahertz mechanical range. If you pump detuned from resonance by about the mechanical oscillator's resonance frequency, you get a linear interaction between mechanical motion and microwave fields at the circuit's resonance frequency. You can think about this in the language of 3-wave mixing, or if you like, in the as Raman spectroscopy, but it's Raman spectroscopy of a single degree of freedom, where the laser is actually at microwave frequencies. So we get processes where the pump photon can be combined with the mechanical oscillator's phonon to make one more photon at microwave frequencies, and sort of processes where microwave photons split up into a lower energy pump photon and into a mechanical oscillator phonon. And you get a linear interaction between these 2 harmonic oscillators, enhanced in rate by the strength of that pump amplitude. And with that as a tool, what you can do is signal processing, kind of microwave fields, using the mechanical element as a signal processing element, much like the classical way that acoustical systems are used. For example, you can take a pulse of microwave field here with an envelope that's turns on suddenly and then decays exponentially in time. You can convert all of the energy and information in that microwave pulse that's incident on a circuit like this, you can convert it into mechanical motion, store it there for a period of time, and then convert it back into a microwave pulse where the envelope, the temporal envelope has been changed, the delay is changed, it's now shifted in time, and in fact, you can even shift the frequency. You can also generate entanglement between microwave fields and mechanical modes. You can use these objects as quantum limited linear amplifiers of microwave signals. Those are kind of things that we worked out over the past 10 years. The big application in this world for us now, the thing which we are working very hard towards, is combining electromechanical and optomechanical systems for the specific purpose of creating a linear converter that takes microwave signals and converts the information in them to optical signals. Basically, just a kind of linear electro-optic converter that works in the quantum regime, which doesn't destroy quantum information. The concept is sort of sketched here. It's one of these electromechanical systems where the vibrating object, the thing that's modulating the inductor capacitor resonant circuit, it is also a part of the vibrational mode is sitting in the waist of a high finesse optical cavity and modulating the resonance frequency of that object. And then by pumping both the electrical circuit and the optical cavity off resonance, you create a linear conversion between microwave fields that enter this microwave port and optical signals that exit the optical port, and vice versa. This is kind of a cartoonish picture of what the object looks like, sketched by a graphic artist, and actually a picture of the things that we make in the clean room that do this kind of conversion. Sitting in the center here is this little square. That's a thin sheet of suspended silicon nitride with a little patch of metal that's been fabricated on it. And that gives us this special mechanical mode, which is both electrically and optically coupled. So our result from a few years ago now demonstrated that we could convert with photons from the microwave to the optical domain with an efficiency of about 47%, meaning that if we squirted in one more microwave photon, on average, you'd get half of an optical photon out. But along with that comes something like 34 noisy photons, much bigger than one, which is about where it would need to be for quantum conversion, but about 100 times better than the previous result. So the conversion has gotten substantially better since then. That's what's actively happening in the group right now. I'll maybe tell you that story in a few months. Motivation for that linear microwave to optical converter is really the construction of a quantum communication network. Here, in a very futuristic notion, you might imagine that you have nodes of that process and store quantum information in the superconducting circuit domain and links that establish entanglement between them. And then you would have a network in which entanglement is shared over that whole network. But what I promised you in the beginning of this talk is that I was going to tell you something about phonons, about accessing individual quanta of sound. And nothing about this linear coupling story accesses phonons. In particular, I've plotted here two representations of the quantum states of harmonic oscillators, two different ways of picturing them. And there's the one that we learn in undergraduate textbooks, where we think about the state of the harmonic oscillator as being in quantum superpositions of energy eigenstates. And then it's just the simplest thing in the world to imagine that you could prepare the system in a particular energy eigenstate. And you can do that for example, if you have the ability to make a projective measurement of the energy of the system. But in everything I've told you about, in fact, end up inferring things which are essentially position and momentum variables of the harmonic oscillator. And in that world, the notion of a single quantum of excitation in a linear harmonic oscillator is a little bit hard to access. Instead, you're much better off describing the system as some quantum blob of noise at the end of a kind of classical stick of displacement. And to access single phonons, you need some kind of strong nonlinearity. It might be a nonlinearity provided by measurement, but everything I've shown you so far, we've ended up only accessing linear equations of motion, linear measurement, and initial states that are Gaussian in character. So can we break out of that? Can we really access single phonon? Well, the electromechanical coupling that I've told you about, it is intrinsically nonlinear. It is fundamentally a nonlinear interaction. The interaction classically is related to the square of the voltage between the plates of the capacitor. That's the going to create a force proportional to the square of the voltage that acts on the displacement of the oscillator. And so in a quantum language, that's microwave photon number, A dagger A, coupled to mechanical displacement, B dagger plus B. Not a linear interaction. It's got three little accretion and annihilation operators in it. But this small parameter appears out front, and that's why the scale is only a few hundred hertz. So we'll need a stronger interaction. Let's say this. If you really like, another way to understand that this interaction is going to be weak is that the vacuum coupling here is really the product of two vacuums. The vacuum, the 0-point motion of this mechanical oscillator, is wiggling and pulling on the 0-point energy stored in this LC circuit. So one way to boost the interaction, well, you can store energy in the electrical circuit by application of a DC voltage, which is now much bigger than vacuum fluctuation. That's an avenue we've pursued. Another thing that you can do is you can have a better vacuum. You can have like a condensed matter vacuum. Specifically, you can slide a slab of piezoelectric material between those two capacitor plates. And now when you squeeze them, they make a pretty decent sized voltage. It turns out that either of these two approaches give you a scale of interaction that we've demonstrated in the group of about 10 megahertz, much bigger than that 200 hertz. You have, however, gone back to a linear interaction. Now the essential coupling between electricity and motion is bilinear in the creation and annihilation operators. You're back to a linear interaction. But the prescription is pretty clear. Now you need only replace the inductor here in this circuit with something which is electrically nonlinear, and in the superconducting circuit world, use a Josephson junction. And so you are building essentially a superconducting qubit coupled to mechanics using piezoelectricity as the thing that mediates the interaction. And that gives you an interaction Hamiltonian like this, where it's really the position of the mechanical oscillator is acting to flip a two-level system associated with this nonlinear circuit. So the particular choice of superconducting qubit, it's in some sense the conventional choice these days, is called a transbon. It's really just an inductor capacitor resonant circuit where the inductor has been replaced with a Josephson junction, which looks inductor-like in the sense that for this flux coordinate across it, the cosine-like potential of the Josephson junction looks approximately parabolic for small flux, and then you can see the deviation, and that gives you an anharmonic potential. Physically, it's two superconducting electrodes separated by a thin insulating barrier. That makes the Josephson junction. You connect them to big metal panels, and that gives you enough capacitance. And in order to isolate that so it doesn't radiate away and allow you to also control and measure that two-level system, you put it inside of a microwave cavity. And you build your world around the lowest two levels in that anharmonic potential, and that's the superconducting qubit. So now superconducting qubits coupled to piezoelectric materials, that is now its own little subfield of quantum science, now known as circuit quantum acoustodynamics. The initial big step taken in that world is this kind of cataclysmic result from the Cleland group about 10 years ago now, where they built a metal piezoelectric metal sandwich, thin little piezoelectric material between, and the acoustical dilatational mode, because it's piezoelectric, would also create potential differences across those metal electrodes, and those were then coupled to a superconducting qubit. The kind of quality of the acoustics got a fair bit better some years later with a result from the Yale group, which launched sound underneath one of these transmon qubits sitting on its sapphire substrate by putting a little disk of piezoelectric material underneath one of these paddles. And then there's also results using not the bulk sound moving through the full thickness of the material, but using sound waves confined to a surface. And that's where our group has focused its efforts. And there's also work from several other groups, including now Andrew Cleland's group, since moving to Chicago. In all of these examples, the key parameter was achieved. A key kind of coupling was achieved in the sense that the rate at which superconducting circuits, the qubits, and the mechanical oscillators would exchange energy, that was bigger than either of the two dissipative rates, faster than the mechanical oscillator would lose energy, and faster than the qubit would dephase, or suffer decoherence. And that puts you into the so-called strong coupling regime of circuit quantum acoustodynamics, a kind of prerequisite really for doing a lot of quantum things. Now, in these examples, the superconducting qubit and the acoustical system, they were studied in a regime where the qubit and the acoustical system were in resonance with one another. And there's absolutely the ability to access phonons in that world. But when these systems are resonant, their eigenmodes, the eigenmodes of the system, aren't really acoustical and qubit anymore. They're uniform admixtures or linear superpositions. Whimsically, you can think of them as qtons and Phon bits. So to preserve the acoustical character, to preserve the notion of a phonon, but still interact with the superconducting qubit, what you'd like to do is work in a regime where the qubit is far detuned from the cavity. And then this underlying Rabi Hamiltonian, you can expand or describe it in a small parameter, which is the interaction strength divided by the detuning. And the kind of first non-trivial term in that expansion is just a coupling between the energy of the superconducting qubit and the number of phonons in the mechanical oscillator in the acoustical resonance, with a coefficient which is now this dispersive shift. And necessarily that's somewhat smaller, about at least 10 times smaller than this bare coupling rate. So you'd like now to have the harder condition of being in the strong dispersive regime where this dispersive shift is bigger than either of the dissipative rates. So I'm going to show you how we can access these individual phonons, where we can measure and detect the presence and absence of single quanta of sound in acoustical resonators. And I'll do that in the context of these surface confined waves. Physicists might refer to them as Rayleigh waves. Engineers have won the naming battle, and they're now called surface acoustic waves or SAW waves. To say a little bit about that, the idea is that at the surface of really any elastic material, there are solutions to the equations of elasticity that are confined entirely to the surface, essentially because the surface is softer, more compliant than the bulk. And so in the dispersion relation, they're just kind of wavelengths and frequencies that exist only at the surface, known as Rayleigh waves and saw waves. This is a little animation showing the excitation of saw waves on a piezoelectric material by some electrodes that are electrically excited, and you can then see the strain field that generates in the color axis, and then the propagation away on the surface. So you have a wave of strain moving along the surface of a material. To make an acoustical resonator out of that, you'd like a mirror. You can do that by interrupting the surface in some way, for example, by putting down little stripes of material. If you have lots of them, then you can meet the Bragg condition where the spacing between those stripes is half the acoustical wavelength, and that gives you a very highly reflective mirror. Same principle as in optics. You put two such mirrors back to back, and the region in between now has confined acoustical modes. It's an acoustical resonator for these surface confined waves. If you do this on a piezoelectric substrate, then the stress and strain at the surface leads to the accumulation of charge, and that lets you couple to these waves electrically. You can fabricate little metal stripes on the surface and induce strain, launch waves by applying voltage between these interdigitated fingers, and consequently a passing wave of strain will also create an electrical signal that you can detect. These are known as interdigitated transducers, or IDTs. So here's a picture of kind of an early device that we made to begin to investigate this circuit quantum acoustics domain. There are a pair of Bragg mirrors fabricated in superconducting aluminum, and that's all of the colored stuff, sitting on an insulating gallium arsenide substrate. Gallium arsenide is a weak piezoelectric material. That creates an acoustical cavity between these two mirrors. We can inject and extract sound through these interdigital transducers and this microwave transmission line. And there's also a superconducting qubit with its own interdigital transducer so that it can couple to sound. So if we zoom in a little on the Bragg mirrors, you can see that the spacing between the stripes here is submicron, meaning that we're going to have a kind of reflectivity of those mirrors around 4 gigahertz and a bandwidth of about 50 megahertz. The superconducting qubit, the Josephson junction, we've split it into 2 pieces, into 2 arms making a loop, and you can tune the transition frequency, the Larmor frequency of that 2-level system, just by threading magnetic flux to this loop. From the lengths involved, you can identify that this cavity will have a free spectral range of 4.8 megahertz. Let me emphasize that this is a microwave frequency system resonant at about 4 gigahertz. If you were to make this resonance at 4 gigahertz electrically and try to get a free spectral range of about 5 megahertz, accessing lots of longitudinal modes, it would need to be something like 10 meters long. This is really taking advantage of the slow speed of sound to make a very compact multi-mode system. I'll mention also, because it comes up in questions a lot, but this little diagonal stripes you see, that's just a moire pattern formed by the registration of the scanning electron microscope against the periodicity of the underlying Bragg mirrors. Okay, so you can measure a system like that basically by injecting sound into the cavity and seeing what is reflected back to you. So measurement really proceeds by injecting a microwave tone into the interdigital transducer, exciting the cavity, letting it rattle around, turn back into electricity, and then be directed out through an amplifier chain. You can just look at the linear response of the cavity or the many cavity modes. And we'll start out by detuning the qubit out of the range of the acoustical resonances. We'll just use this little flux control to detune the qubit. When we look at the reflection, what we see is a family of dips, each one corresponding to a longitudinal resonance of that acoustical resonator. The free spectral range is indeed about 5 megahertz, and you can see that the line widths of the resonances, their internal loss rates is something like 100 kilohertz. You can also see the mirror bandwidth, as well as the bandwidth of the IDT a little bit in the fact that we see these over a 50 megahertz range. And now what we're going to do is look at what happens to these resonances as we begin to tune the qubit as we bring the qubit into resonance with these longitudinal modes. So here is the same sort of reflectance data plotted in a color scale with the spectroscopic frequency on the y-axis and the magnetic control of the qubit frequency on the x-axis. You can see little regions where there's a whole family of avoided crossings. And if we kind of make a frequency domain picture, the frequency on the y-axis here, the qubit is tuning over a very wide range, many gigahertz as a function of the magnetic flux we introduce. And in a very narrow range in this picture here, it is in resonance with this the acoustical cavity. And you can see the kind of qubit resonance passing through that family of acoustical resonances and seeing, in fact, avoided crossings, indicating some kind of coherent coupling. You can zoom in on that in a little more detail and see a family of these avoided crossings. They have particular strengths and weaknesses, disappearances and appearances that you can understand. I think the first thing to emphasize is that we are indeed in the strong coupling with this device, in the sense that we can determine the electromechanical or qubit mechanical coupling rate to be about 6.5 megahertz, and that's contrasted with the dissipative rates of something like 100 or 200 kilohertz and about a megahertz for the intrinsic qubit line width. I think the thing that really jumps out to us a little more drastically, though, once we've been pleased with ourselves for reaching the strong coupling limit, is that the coupling strength is also comparable to or larger than the free spectral range in this cavity, really indicating that we're in a deeply multimode limit. The qubit is not so much becoming hybridized with one mode of the acoustical system, so much as it's mediating the coupling between two modes. And in fact, in any place in this range of frequencies, the eigenmode of the system never has very much qubit character. It's just diluted by the presence of all of these other modes to which it is sufficiently strongly coupled. That's interesting, but it does mean that reaching the strong dispersive limit is challenging, because there's no place anywhere in this range of frequencies where the qubit is detuned by more than its coupling strength from any longitudinal resonance. You're always effectively resonant with at least one longitudinal mode. So here, the acoustical world has given us this playground of many acoustical resonances in a compact structure, but it's forced us to think about what to do about that. And in particular, reaching the strong dispersive regime is a little bit hindered in this multi-mode world for the simple reason that in order to be in the dispersive limit, you need the detuning to be large compared to the coupling. But you'd also like this dispersive shift to be big, as big as you can make it, because their dissipative rates in this problem, they're not going to be zero. You need to have them be big enough. And what it really means is that in order to, if you would like to be in the strong dispersive regime, you need to make the coupling rate small compared to the free spectral range. And in doing that, you might end up being small compared to dissipative rates in the problem, or at least not that big. And that's in the case where you would couple uniformly to all of these longitudinal modes. But what acoustic takes away in one sense, it gives back in another. Using the ability to structure and shape the interdigital transducers, it's going to be possible to create a non-uniform coupling such that longitudinal modes that are close to the qubit frequency will be more weakly coupled, and as you get further away, more dispersive, you get more strongly coupled. And in that sense, you can have a scale for the coupling which is big, but suppress the coupling to nearby modes. How do we do that? I think this is really the power of working with surface acoustic wave devices. You have a very flexible design space, allowing you to shape your interdigital transducer lots of different ways. And the idea here is simply to use the surface acoustic wave equivalent of double slit diffraction. We split the transducer, the interdigital transducer, into two half transducers. You can understand that that's going to give you a kind of interesting frequency dependence. If you were to make a little electrical impulse, you would launch sound, where that traveling sound wave would really be composed of two blocks of strain. Fourier transformed, that would give you something which would have this characteristic double slit interference pattern of a sine of x over x envelope associated with the width of these half transducers, and sharp interference associated with the distance between them. And so now that is going to be mapped into the way that the qubit couples to sound waves. Indeed, we build exactly a device like this, where the qubit interdigital transducer is split into two and sits in the between the mirrors of a cavity. Here's the qubit, two mirrors, the split IDTs with their width d, their separation s, and then the cavity length l. The coupling, if you were to say, given that if I took away the mirrors, you could calculate the following thing. You would say, at what rate will my qubit decay to its ground state because of its coupling to sound? And that is a very frequency dependent quantity. It has exactly this kind of Fourier constructed double slit interference pattern. We arrange for the mirror bandwidth here to lie essentially between these first two nulls of that coupling, where the emission, the decay of the qubit to its ground state is really nulled by the interference between these two half transducers. Those are the confined waves. If you zoom in on that, you get a few set of longitudinal modes. You park your qubit here at the null and its coupling to sound waves, and it is still dispersively coupled to these longitudinal modes, where the strength of coupling grows with the detuning. To couple to the whole system electrically, we put two big paddles on the qubit, and that way we can talk to the qubit electrically, controlling and measuring its state. So now we do qubit spectroscopy. We don't measure the cavity and infer the qubit. We measure the qubit and infer the cavity. So we're just going to excite the qubit, or try to excite it spectroscopically on the y-axis as a function of its resonance frequency being tuned on the x-axis, and then the probability of being in the excited state in the color axis. And what you can see is, as we tune the qubit through, we see a whole family of avoided crossings, each one associated with one of these longitudinal modes. And up here, the qubit is decoupled from acoustics in a resonant sense. It can't emit or decay into sound, but it's still dispersively coupled to these longitudinal modes. And we can identify these three strongly coupled modes. If we excite the qubit spectroscopically near resonance, well, we've seen that. As we tune far from resonance, you can also begin to excite the qubit because it inherits a little bit of the cavity to which it's dispersively coupled. You have to drive much stronger, but you can see that. And you can identify the acoustic line widths. And in fact, you're dispersive with respect to all of these modes. And now we're going to excite the acoustic modes, pump some energy into them, and see what that does to the qubit spectrum. The nice Lorentzian peak of the qubit now breaks up into little satellite peaks. Each one of those satellite peaks corresponds to the qubit's resonance with in the presence of one more phonon, one more excitation inside of the cavity. So this is the kind of 0 phonon transition of the qubit. Here's the 1 phonon transition, the 2 phonon transition, and maybe just barely a 3. And the family of curves is just larger excitation of the acoustical, or sorry, larger excitation of the acoustical cavity. The fact that you can see the qubit line width really break up into these discrete features associated with the presence or absence of single phonons is direct evidence of breaching the strong dispersive regime. And it's nice because it's not only for one of these modes, it's really a multi-mode system. You can be in the strong dispersive regime for the same qubit detuning simultaneously for several of the modes. So now I like to say that sound waves, they're particles. This is in some sense, directly resolving the particle-like nature of sound, of phonons. But those particles, they're also have a wave-like character that we can see directly in an experiment like this. So to illustrate that, think about the qubit spectroscopy here. As we tune the qubit, it has a resonance frequency that we would expect in the absence of its coupling to these acoustical modes, sort of represented by this yellow line. And now we can subtract away that dependence and just look at the deviation plotted here as a function of frequency. The region here in the center, the region here shown is just the center of this kind of deviation from expected qubit resonance, where we have coupling to the transverse modes. As we get outside, coupling to the longitudinal modes. As we get outside of the region over which the mirrors are reflective, outside of the confined modes, you can see that the qubit line width is very strongly frequency dependent. And in fact, we can excite the qubit and measure the rate at which it decays, and that's plotted here. And it has this very strong double slit interference pattern. This is just wave interference, but it's the wave interference of one phonon emitted by the decay of the qubit in its excited state. Maybe in our modern world of quantum technology, we have become a little jaded and dismissive of such 20th century notions of wave particle duality and complementarity. Nevertheless, I think the fact that we can see both the particle-like nature of sound waves and the wave-like nature of phonons in the same device, I find extraordinarily appealing. I'll mention also that you can see that as you detune the qubit, not only does its line width change, but its resonance frequency is changed. Of course, those are related necessarily by a Kramers-Kronig relation. But in atomic physics language, this is the frequency shift of our two-level atom associated with making its coupling to a continuum of radiant modes stronger or weaker. It is the Lamb shift. It's the Lamb shift of acoustical coupling. All right. I think with that, I will skip the last two slides here because I can see that I'm pretty much out of time, and just wrap up. That has shown you that we have linear quantum electromechanics. We've taken that kind of concept to the point that we can resolve single acoustical phonons. Our acoustical qubits can really have designer coupling, and we can observe things like acoustic Purcell effect, acoustic Lamb shift, acoustic Stark shift. This is kind of the folks who've paid for the work, and a snapshot of current group members or recently departed group members who are involved in the work. Thanks very much.
Thanks for the nice talk, Konrad. So there was a question in the chat box at the beginning of the talk, asking about the quality factors of the drum type of resonators.
So the drum resonators, they have a quality factor of around a few 100,000, maybe. We have seen close to, but never quite broken 1 million in those drum resonators. Let's see, the context for that is maybe to say that we think that quantum information can live in the mechanical motion, in the mode before a thermal phonon would enter and destroy that for a period in excess of 100 microseconds, but at the moment, not much more than that. Let's see, I can see chat questions coming in. Would you like me to answer the chat questions directly?
Yeah, please.
Okay. So Paul asks me, what's the prospect of pushing the noise in the optical to microwave transaction below 1? Generally excellent. Paul, there's been a lot of kind of technical progress on improving various parts of the concept, and we have sort of been reaping the benefits of those improvements in the past 6 months. I won't sort of plant my flag on a number yet, but say that things are at least 10 times better than what I was showing just very briefly in there, and then the 2018 result. And maybe most importantly, the nasty thing that you might have worried that happens, that basically, look, you have an intense laser light field in close proximity to a superconducting circuit, and that has to be bad. Well, yes, but the bad part of it we can see, but only when we turn up the laser far greater than we would need to reach the regime of kind of quantum transduction with at least 1 kilohertz or 2 of bandwidth. And let's see, where was that picture? I should be talking over a relevant photograph. Here we are. So the thing which we've really gotten control over now is scattered light from an intense laser light field landing on the superconducting circuit and breaking Cooper pairs, making electrical noise. That was certainly a big problem in previous concepts, and really we seem to have tamed that. Yes, there is a sense of transducing the qubit. So it's just sort of not that interesting to upconvert a coherent microwave field. We have put a superconducting qubit into the experiment. We are able to do things like, one of the things which maybe I can tell you is that the superconducting qubit doesn't appear to suffer any bad things from the fact that it's coupled to one of these electro-optic converters. We can do things like read out the state of the superconducting qubit optically. That's not quite encoding the state. Well, it is in fact encoding the state of qubit in a propagating microwave field. It's probably not the right way to do that. So the prospects are also good for that in the sense that the technical parts of putting it all together we've done, and it works. And the qubit so far is blissfully insensitive to the fact that we're stabbing the cryostat with an intense laser light field. Could we modify the current experiments to execute gate operations using saws or to transport quantum information? Yes. So the gate operations using, so the way to say that is the following. Doing gate operations on the phonons, which is definitely where we'd like to get to say we're going to do things like treat the longitudinal acoustical modes as things that can encode qubits and access that full Hilbert space. Your ability to do that is almost reflected. You can almost read it off from the visibility in peaks like this. And if you were to say, how well can you really control the Hilbert space of one of these longitudinal modes? The answer to that is about as well as you can resolve that this is a peak, and not that well, frankly. I mean, you can resolve it, but it's not a sharp peak with a big desert of no qubit response, and then the next peak. It's kind of, all these are mushing into each other. Tells us that the coherence of the acoustical cavities and frankly the qubits in these acoustical devices has to get much better. And that's where our focus has been. That's what we've been working on very much recently. I won't say too much about that other than we know that diffraction is a thing that happens, and if you're an optically trained person, a cavity that looks like this is sort of hilarious. It's two flat mirrors separated by much more than the width of the mirrors. Such a thing is an unstable cavity, and even if it were magically stabilized, the diffraction has to kill you. It's not quite that bad because there's a little bit of anisotropy in the propagation of sound waves in these systems that actually confine the spread of the longitudinal modes a little bit. But of course, you ultimately need to make curved mirrors and to make stable cavities. The only difficulty is you have to do that in a medium which is anisotropic. And that's actually quite an interesting problem. A lot of our attention is going to that problem now. The thing I can say is that we certainly can make cavities now that have line widths less than 2 kilohertz. Okay, let's see. Other questions in the chat?
I guess that's all.
I think I got the questions. Yeah.
Yeah. Cool. So we are well past the noon. So thank you again. Thank you for the very nice talk. I guess next week we'll also have